Good morning, good afternoon, or good evening, wherever you are located, and welcome along to the AMETEK Solidstate Controls webinar this month for November 2025. And this month it is on the differences between the CVT, which is a constant voltage transformer technology that we supply, versus the PWM pulse width modulated inverters that we designed. So basically the pros and cons of each, how they work, how you can tell the difference, all that good stuff. Before we go any further, I'd just like to ask, as I always do, if you can hear my voice. It would be great if you look on the right hand side of your screen. You should see the chat function. If you can type in there, if you can hear my voice, that would be fantastic. And that also allows everybody else to join perfectly. Thank you, London. I appreciate it. So if London can hear us, that means everybody else can hear us. So I will move on to the next slide and do some introductions. So my name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solidstate Controls, located in the Stafford location, which is on the southwest side of Houston. I have, actually, this is an older slide. So I have 25 years in the industrial UPS industry. I've worked in the North Sea oil and gas on the platforms, been on way too many helicopters. And then I moved over to the United States, and I've worked in the Gulf Coast, and I've worked on all different types of manufacturers and models of UPSs and chargers. There will be a lag of around about 30 seconds between you hearing my voice and me seeing a question. We use a platform called Webinar Jam, and basically it takes the signal that I am creating at this moment in time, and then it has to turn that into Android, Apple, and Windows-based signals. So there is a little bit of processing that goes on. So it takes some time to do that. So when I speak, you hear my voice approximately 15 to 30 seconds after I've spoken. So if you have a question on something that I have said, I'm only going to see it 15 to 30 seconds after I've spoken. So what I ask everybody to do is, if you look on the right-hand side in the chat bar, there is the chat function, and there is also the Q&A function. If you have a question at any point during the webinar, please put it in the Q&A tab. And then at the end, I will go through everybody's questions one by one and hopefully answer them at that point. It just helps with the flow of the webinar as we go through. The platform that we use does have a panic button. So if something does go wrong, if there is for some reason a comment that you can't hear or see the slides anymore, then I can press the panic button. Everybody gets ejected and a new room is created. It's all done seamlessly, and we should be able to carry on from where we left off without any issues. A very popular question we keep getting asked is, will the webinar be recorded? And the answer to that is yes. The webinar is recorded. We have two versions. The first version you will automatically get from the webinar platform, and they will send you a link after the webinar is completed, and basically it allows you to watch the webinar again as if it was a webinar. In other words, you can't really fast forward, rewind, pause, and do all that kind of stuff. But what London does, and she's put it in the chat bar there, thank you, London, is a link to our YouTube site. And what our fantastic marketing department do is they take that video, they convert it to an MP4, and then upload it to the AMETEK SCI YouTube site. And that way you can watch it, play, share, do whatever you want to do. It is public facing. There are no restrictions. You can do whatever you want with that video. Okay. And the link is there in the chat bar. And the last thing is, how long will the webinar last? The plan is it should last round about 1 hour, but it depends how many questions we get, and obviously how much I talk. And I tend to talk a lot. I try not to, but I try to stay on topic, but we will see how it goes. But I do appreciate you taking the time out today to watch this webinar. So let us get started. So the learning outcomes today are going to be understand basic inverter design, understand the two solid-state controls designs that we use in our inverter bridges, the two main ones, discuss the components used. We're going to discuss something called desaturation for our pulse width modulated UPS systems, and then discuss the benefits and drawbacks of both designs. So that is the plan. So the first thing is, what is an inverter? We need to know what that is before we go any further. In its most simplest form, an inverter is something that converts DC into AC. Okay, and it's usually done with semiconductor switching, which we'll go into in just a moment. But in its most basic form, an inverter converts DC, usually from a battery and a charger, and converts that stored power into AC to keep AC circuits backed up if there is a power outage or any power dips whatsoever. Okay, and the technology of choice for inverters is what's called an IGBT, which is an insulated gate bipolar transistor. An IGBT, and that's the representation of it on the screen there. We have a gate, we have a collector, and we have an emitter. Okay, and the easiest way to look at a transistor is this way here. I know you shouldn't touch electricity, so don't do this at home. But in its most basic form, a transistor is a switch. Okay, if you send a signal to the gate, and it's a voltage signal for an IGBT, and it has to be within the parameters given on the data sheet for that particular IGBT. But if you send a correct signal to it, it's as if this finger is going to press this spring-loaded switch into the on position. Okay, so if we send a gate signal, this switch moves to this point here, and the collector and the emitter become connected together. Okay, so it really is as simple as thinking of it as a momentary switch. Okay, and then if you remove the gate signal, then the spring pushes the switch back into the off position, and the collector and the emitter are no longer connected together. Now, this is the mechanical representation. This in no way, shape, or form tells you exactly how the IGBT works and how it is done, but just for your mind on an easy way to how to think of what an IGBT does, I think this is the most simplest and easy to understand methods of understanding what the IGBT does. So hopefully that works for you. And this is what the IGBTs inside our UPS looks like. This pack here only has one IGBT in it, and this pack here has two IGBTs. It's very difficult to see on the screen here, but there's one there and one there, and they share one of these terminals together. Okay, and that way they're basically designed in such a way, these dual packs, where you can put them inside an inverter bridge and they are ready to go pretty much. It makes it easy for you to modularize an inverter bridge. Okay, but that is what the inverters, the IGBTs inside our inverters look like. And that's what they should not look like. That is the inside of an IGBT that has been catastrophically damaged. And that is one of the downfalls of IGBTs is although they are getting more and more robust as technology moves on, they can be very sensitive to extremely high current. In other words, short circuits on the output. So we have to come up with ways on how to try and protect the IGBTs from basically self-destructing. And we do quite a good job of it, okay? But we definitely don't want to see an IGBT like that inside your inverter bridge. So the first design that we're going to talk about is what AMETEK Solidstate Controls calls our micro SE or DSE inverter. Okay, it's our ferroresonant design or our constant voltage transformer design. So this portion here is what we call our CVT, our constant voltage transformer. And what a constant voltage transformer does is, for varying inputs on the primary, so the primary can go up or down, the secondary at this AC output here is kept constant. Okay, so for certain parameter of input fluctuations, the output is kept constant. Okay, so that is what the transformer is doing. So in truth, in this design, the inverter bridge does switch the DC back into AC, but it is the constant voltage transformer that does the majority of the regulation. In other words, how that AC is kept at a constant value. And we'll go on to show how that works. And it's done with this C805 and these all these different windings. Some of them are summing windings, some of them are compensation windings, and basically it's tuned in such a way that the transformer goes into its saturation region. And basically, once you get the transformer into its saturation region, then the output can't change very much. So that is what we're trying to do with the capacitor and the windings on this transformer. It's kind of complex, and we do have a white paper on our website that tells you more about how a ferroresonant or a CVT, a constant voltage transformer, works. Okay, but this is what a simple single phase transformer looks like. So this transformer here is pretty much exactly a representation of this transformer here. Okay, there are lots of different windings coming off the transformer with different purposes, and we then have to connect that to the capacitor bank into the output and get it to do all of its wonderful magical things. But the important thing is to remember is you can have varying voltage going into the primary of a constant voltage transformer, and the output remains constant at a certain value. For a 120 volt system, it's going to stay around about 120 volts for varying inputs. Okay, well, how do you tell the difference? It's a very common question that we get. How do I know if I have a microferro system, a ferroresonant system, or how do I know if I've got a PWM, a pulse width modulated system? And it used to be quite easy. You used to be able to look at the front of the UPS, and if you saw this placard here that has LEDs on it and the push buttons in this way, and there is no electronic screen, it's just this placard here, then you knew you had a constant voltage transformer, a ferroresonant system. It was quite simple. But over the last 3 to 5 years, we came up with a new system that still uses the CVT transformer. But now what we've moved to is a system that's very similar to our PWM inverter that has a touch screen on it. So it does get a little bit complex. You can't just look at the front anymore and say, oh, okay, I have this white placard. It's a ferroresonant system. Yes, that is correct. But you can't now say, oh, I've got a screen, so this must be a PWM inverter. That's not correct anymore. What you have to do is you have to look at the rating plate, this sticker here. And if you go and blow it up, you can see we have this term here. This is the SE. So whenever you see an SE, then you know your UPS has a ferroresonant system, has the constant voltage transformer inside. Okay, so for the older systems, the SE is for the ones that look like this. Okay, and then the ones with the screen that look like this are called a DSE. and I'll show you the rating plate. So you can see it says DSE. Now this is for the model number, not for the part number. This is for the model number. So whenever you see DSE or SE, you know that the system has a constant voltage transformer or a ferroresonant transformer inside. Those terms are interchangeable, CVT, ferroresonant, okay? And also, the sound is different between a ferroresonant system and a PWM. The sound for a ferroresonant system is a 50 hertz low frequency humming sound. It kind of sounds like it's low frequency, and it's quite distinct, and it's quite loud in some cases, compared to a PWM system, which switches at 8 kilohertz. So the frequency that you hear is a 8 kilohertz whine. It's kind of like an ee sound. So the sound is very, very different between the two technologies. Okay. Now, for the ferroresonant system, I've tried to make it as simple as possible. So I've just got the primary of the CVT or ferroresonant transformer here. But this is actually how we switch the DC into AC. So basically back here, this is a positive and a negative, and we have our battery connected here. Okay. And then what we do is we will switch one of these IGBTs on at each time. So let's say we're going to switch Q1 on. So we're going to turn Q1 on. What happens is that allows power to go through here, down to this center point here, and then we have to get back to the negative of the system here. So that would go back up through this transformer winding, through Q1, and back here. So what we would get is if we sent a pulse at this point here, we would get a pulse going this way, okay? And then what we would do is we would switch Q2 on, and we would go down this way here, and we'd get through Q2 and get back to the negative here, and that would give us the other side. And what we do is we switch that, and we create a square wave on the input at 60 hertz. I said 50 earlier, that's my Europeanness coming through. It's at 60 hertz for a ferroresonant system in the US. Okay, so all we're doing is quite simple. The inverter bridge on a ferroresonant system is very, very simple. It's saying, okay, I'm going to switch Q1 on and then Q2 on, and we're going to do it at 60 hertz, and we are going to create a square wave that goes into the primary of the transformer. Okay, that's all the inverter does. It's very simple. And then the transformer smooths that square wave out on the secondary into a nice sine wave, and it also maintains the output on a single phase system at 120 volts. Because you've got to remember, this is coming from a battery. So whenever you have a battery connected, if we do lose power to that battery, the voltage is going to start going down, which means the voltage available into this transformer here starts going down. So the square wave size, the peaks of the square wave are going to change. And you can see that here. So we're creating this 60 hertz square wave, but the size of the square wave is based on the DC voltage from the battery. And on this one here, we made it quite simple. We made it 100 volts peak or 200 volts peak to peak. So let's say this is a 100 volt battery because it's easy. 100 volts is a nice easy number. Then we're switching one side at 100 volts. So let's just say that's this side here. Excuse my terrible scribbling. And then when we switch this one on here, we go down this way through that, and we get the bottom half, okay? And what happens is when the battery starts discharging, this voltage can go down, and this voltage here would go down. So the square wave size can actually go down. And we don't want the output of the transformer, the sine wave output, to change. So what this transformer does is for the changing DC the pulsed square wave that goes into the primary of the transformer, although its amplitude will change, the amplitude of the secondary, due to the constant voltage nature of the ferroresonant transformer, the output does not change. Okay? And the easy way to think about it is exactly how it's drawn here, with switches instead of IGBTs. And there's the ferroresonant transformer there. So once again, if we close S1, the transformer, we get, in truth, it's actually the negative portion of the square wave that way there, which would give us, on this output here, that would give us a negative portion of the sine wave. And then if we close S2, it goes down this way here. That makes a positive square wave here, which would make the positive half of the sine wave there. Okay. And I know this drawing is very, very busy. I do understand that. But it's exactly the same drawing. We have, this is actually one of our ferroresonant bridges. So we have our battery connected here. Okay. There is the center tie point of the transformer there. Like I said, I know it's very difficult to see, but we have Q1 and Q3 here, and we have Q2 and Q4 here. So if we switch this pair of IGBTs on, we will go through this way, through the transformer and back to negative that way. Once again, that gives us the square wave going that way. And then if we switch Q2 and Q4 on, it will go down through this transformer, out through that way there. That gives us our positive half. And then the result out of the system here is our sine wave. Okay. That is the ferroresonant transformer there, and we get a sine wave out. And that is a constant voltage sine wave. Okay. Now we do, on the microfarad system, we do have some CTs that are connected on the inverter bridge. Now, if you remember earlier, I mentioned that IGBTs are very sensitive to high current. Okay. And what we do is we do monitor the current. Now let's take a step back. Let's say, just for ease, let's say these are 100 amp IGBTs, and for simplicity, we're going to say if they see more than 100 amps, they could be destroyed. That's the easiest way to think about it. Okay. What we can do is, if we did have a short circuit on the output here, okay, if something on the load had a short circuit and live to neutral was connected together, then what's going to happen is these IGBTs, we can't regulate that short circuit current. So what the IGBTs are going to do is they will try and supply over 100 amps. And then what happens is these CTs will say, okay, my job, when I see over 100 amps going through the IGBTs, my job is to switch off the gate signals to these IGBTs to protect them from blowing up. And then what the system will do is, if it does get to that value, it will transfer the system to bypass through the static switch. And then it shuts down the IGBTs to try and protect them. But the really good thing about a CVT, or a constant voltage transformer, is it has some stored energy. It can actually supply power once the IGBTs are turned off for about half a cycle. Okay, so what that allows us to do, this stored energy in the IGBTs, sorry, in the transformer, allows us to transfer to bypass and do that seamlessly with the half cycle of stored energy in this transformer. So your load circuits are not going to see any interruption whatsoever. So that's what these CTs are for. They are to protect the IGBTs from destroying themselves. And the other thing that our modern microfarad systems can do is they can actually change the size of the square wave that goes through. So basically, it makes it a little bit more efficient. So what we can do is we can adjust the pulse width is varied at the trailing edge. So basically, here's the starting point of the square wave here, okay? And we can adjust this trailing edge here. And there's the starting point here. We can adjust this trailing edge here. So what you can see is on the top one, the top waveform, this waveform here, we're not adjusting it and the area under the curve stays the same. But on this bottom one, we're saying at 140 volts peak, which is the equalized voltage for one of our 60-cell lead-acid battery systems, we can go as high as 140 volts. Then we turn the IGBTs off quicker than we do when there's less voltage. And the area under the curve basically becomes the same as that. And then if the battery voltage discharges to 105 volts, we can turn the IGBT on later and make the area under the curve the same as this one here as well. So if you did basically length times height for this, and then length times height for this, the area of that rectangle is going to be exactly the same as the area there. And that allows our transformer to be slightly more efficient. It's not pulse width modulation. All we're doing is it's a modified square wave, basically, is what it's called. Okay, and it allows us to have a little bit more control and a little bit more efficiency out of the ferroresonant system. So, what are the benefits of a DSC bridge or a microfarad bridge? Well, the biggest benefit is it's a very simple control circuit for the inverter IGBTs. The circuit basically tells the IGBTs to switch on and off at 60 hertz or 50 hertz if you're in a 50 hertz country. And there are no other complex regulation circuits such as current limit or voltage control or anything like that. It's basically, I'm going to make a 60 hertz square wave, and then the constant voltage transformer is going to do all of the regulation. So it's a much simpler circuit. It's also very robust. The regulation is performed by the ferroresonant CVT, which is an 80-year-old technology, and it is proven. It just works. Thirdly, the CVT has excellent fault clearing capabilities. It can supply in excess of 500% of the rated current for a very short period of time. So many people who come to our training class say, okay, what happens if our bypass isn't available and we have a short circuit? Because I said previously that the system does try to transfer to bypass to clear a short circuit. Well, with a constant voltage transformer, we can, for a 100 amp system, it can actually supply 500 amps for a very short period of time to try and clear that fault before trying to transfer to bypass if it had to. So there is much more likelihood, there's a much bigger likelihood that a constant voltage system, a CVT system, might clear a fault without having to go to bypass. Also, a CVT has stored energy, which I said previously, which will supply the fault before shutting down the IGBTs. And that prevents the IGBT failure in many, many cases. Okay, so that stored energy in the transformer supplies the fault rather than the current going through the IGBT. And the bridge design has been proven reliable for many, many decades. So that's the advantages of a microfarad system. At the very end, I'm going to do a comparison of the two systems so you can see the benefits and some of the downfalls of both designs. So now we're going to talk about the DPP. And as you can see, this looks very, very similar to the DSE, which is the digital fair resonance system, because it has a screen. And the screen that we use is pretty much exactly the same screen as we use in the DSE for the DPP. This keypad is the same, and this screen here looks the same. So the most important thing, once again, is to look at this foil here to tell you, is it a DSE or is it a DPP? So when we see DPP, that's telling you that it is a PWM system. Okay, digital process power is what DPP stands for, and that is our PWM system. Okay, so whenever you see DPP, that does not have a CVT or a constant voltage transformer in it. And it uses a slightly different design to change the DC into AC. It uses what's called an H bridge, okay, because it looks similar to the letter H, okay? And the easiest way to think about it is we have 4 switches in an H bridge, S1, S2, S3, and S4. And if you think about it this way, rather than have we're not going to supply a transformer in this circumstance. Just to give you an idea of how it works, we're going to supply a motor. So this is our motor. And if we close S1 and S4, and we have our battery positive and negative back here, what that does is that allows power to flow here, and it makes this side of the motor positive, and then our negative goes back this way here. So it makes this side of the motor negative. So what we can say is that will make this motor spin in a clockwise direction, okay? And then if we reverse the system and we close S3 and S2, and S1 and S4 are now open, we still have our positive here, but now we're going to this side of the motor, and that makes that positive. And our negative is now connected through S2 down this way here. And that makes the motor spin in the counterclockwise direction. So we are changing the polarity of this motor, and it's just the same as what we would do in an inverter bridge. We're going to replace that motor here with a transformer, okay? This one here just tells you that we should never ever close S1 and S2, because that would give us the direct short across the battery. So we have controls in place that we never ever close S1 and S2. That's called shoot through, and it prevents the IGBTs from being catastrophically damaged. Okay, so we never want to do that. It's always S1 and S4 or S3 and S2. So this is the exact same circuit, just drawn slightly differently. Remember, we had our motor drawn here, but now what we've done is we've pulled that motor out here and we've made it a transformer. It's still exactly the same drawing. And now we have Q1, Q2, Q3, and Q4 here, okay? And what we would do is if we switch Q1 and Q4 on, the positive will go down this way, make this positive, and then the negative will go down this way and make this negative, okay? So if we stuck to the square wave, that would give us a positive pulse that way, okay? And then if we turn Q3 and Q2 on, that allows this side of the transformer to go positive, and then we get the negative down this way here. So that makes that negative. So we would get our negative going pulse here. So that would, in theory, give us our square wave. But we don't use a square wave in the PWM system because we use the benefits of the high switching frequency of these IGBTs. And what we actually do is we switch the pairs on. We've labeled them here as A, and these ones here as B, exactly the same. We switch it on at 8 kilohertz using pulse width modulation, PWM, okay? Now, in Wikipedia, modulation is in electronics and telecommunications. It's a process of varying one or more properties of a periodic waveform called the carrier signal with a modulating signal that typically contains information to be transmitted. Okay? So most people will know the radio stations that we listen to. In the olden days, it makes me feel old, they used to use AM, which was amplitude modulation. So our carrier signal is here. It does not change, okay? That is, so if you set your radio to 1050 frequency, okay, that is what the frequency of this carrier signal is. But then if we added in our modulating sine wave onto that, what happens is you can see here that as this amplitude starts to go up, the amplitude of the sine wave goes up. So that is amplitude modulation. We're not changing the frequency. You can see here, if you go, oh, my lines aren't very good. If we go down for there, all of the frequencies stay the same. The frequency does not change, okay? It is only the amplitude that is changing. That is what amplitude modulation means. And then obviously in the modern day, we use FM. So we use frequency modulation. So once again, the carrier signal doesn't change, but now it's 103, I can't remember if it's usually megahertz or kilohertz that the radio stations use these days, but that does not change. And then what we do is if we add this carrier signal in here to that, sorry, the modulating sine wave to the carrier signal, then the amplitude does not change. You can see that the amplitude does not change there at all. What's happening now is for this portion here, what we're actually doing is changing the frequency. We're actually lowering the frequency. The frequency is lowering for this point here. And then as we go here, the frequency is increasing. Okay, so this signal that comes out here is a frequency modulated signal because the only thing that is changing in this waveform here is the frequency, not the amplitude. Okay, but we don't use either of those technologies in the PWM system. Okay, we actually change the width of each pulse. So if you look at this section here, okay, what we're trying to do is create a synthetic sine wave. So what we do is we start with a very thin pulse at this point here. Then as you move along, the pulses get wider and wider and wider. The amplitude is not changing. And actually, if you count the center point of all of these pulses, the frequency is not changing either. The only thing that is changing is the width of the pulses. And if you did the mathematical calculation of this section here, you would actually get a representation of a sine wave because the area under the curve of this portion here is very small. And then the area under the curve of these very fat pulses in the middle is very large. So it does represent mathematically a sine wave. And then what we do is we put that through a filtering circuit, an inductor and a capacitor, and it ends up making a very, very nice sine wave on the output. So there is our capacitor there, and there is our transformer, which has inductance. We used to have a separate inductor to work. It was an LC circuit, an inductor capacitor circuit, but now we've put the inductor inside the transformer to get rid of this component here, just for ease, okay? And what we're doing is we're creating a PWM signal, okay? So what we're doing is we're switching these two transistors on and create this to give this. And once again, this is not 8 kilohertz. You know, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's 13 pulses there, and then there's 13 pulses there. So that's 26 pulses per cycle. So that is nowhere near 8 kilohertz. 8 kilohertz means we are switching at 8,000 times a second. Okay, so think about that for a moment. We're switching the IGBTs at 8,000 times a second. Every second of every minute of every hour of every day of every week of every year. And these systems are designed to run for at least 20 years. So for 20 years, we're switching these IGBTs at 8 kilohertz. And for every single one of those pulses that we're switching at 8 kilohertz, we can change the width of this pulse dynamically for every single pulse. So it's very complex circuitry that does that. But what that allows us to do is create a much nicer sine wave, and we have much more control over the regulation of that sine wave. Okay. And here is the inverter bridge here, drawn as it would be in one of our diagrams. And as you can see, we've got, this would be classed as Q1, this would be classed as Q2, this would be classed as Q3, and this would be classed as Q4. Now, bear in mind, there are two IGBTs. We can parallel IGBTs to get more power, but you can just think of it as one IGBT. And what we would do is we would take the positive down through here. It goes down up to this transformer here, and then up, back through this IGBT. And then it's very difficult to see on this, but we get back just Q1 and Q4. So it goes down that way there and out that way. And that would give us our negative pulses on that portion there. And then if we turn Q3 and Q2 on, then we would go down through this IGBT, up through there, and then down back through that IGBT there. And that would give us our positive PWM going in there. Okay. But you have to remember, for any IGBT, a fuse is not fast enough to protect it. Okay. Let's say this is a 100 amp IGBT and you protected it with a fuse here that was a 100 amp fuse. This IGBT is usually going to fail, sometimes catastrophically, before this 100 amp fuse blows. The IGBT is that sensitive. It really doesn't like high amount of currents to flow through it over its rating. So even for the PWM system, we have to come up with a system to be able to switch the IGBT off if we detect high current. And what we use is something called IGBT desaturation. And it's built onto our control board. It's built onto this gate drive PCB here. What it does is it monitors the collector and the emitter voltage. And then we can say whether we're going to send a signal to the gate or not. Okay. So if the IGBT is on in its normal region, once again, if it's a 100 amp IGBT and we are less than 100 amps, then we know that the voltage between the collector and emitter should be within the correct parameters. Okay. And let's say, for example, that should be 0.7 volts. Okay. Then this sensing circuit back here says, okay, when I send a signal to the IGBT and turn it on, I should see no more than 0.7 volts across the collector and the emitter, because an IGBT is never a perfect switch. There is always going to be some voltage drop across it when it is switched on, but it should be limited to a very small amount. Okay, and it's usually about its value. So what that sensing circuit can say is, okay, if this went up to 120 amps, we're now out of our saturation region, and that 0.7 volts may go up to 1.2 volts. I don't know what the value is, I don't know, but that is going to be sensed back here immediately. And what it will do is it say, well, my IGBT is on, I am seeing too much current. So what I'm going to do is, it's actually, it's not 0.7, it's actually 9 volts it's looking for. If I see more than 9 volts, my apologies, across the collector and the emitter, then it's going to immediately switch the IGBT off. Okay, using this control circuit here, much faster than a fuse, much faster than a fuse. So what we're trying to do is find out when this IGBT is out of its saturation region. In other words, it's desaturated and there's too much voltage drop between the collector and the emitter. In this circumstance here, it's more than 9 volts, and it will send a signal to turn that gate off, and 9 times out of 10, it will protect that IGBT from blowing up. Okay? It will give you a desaturation alarm on the control board, and the system will transfer to bypass without any issues whatsoever. And we do that all the time in our training class and in our lab, and it works 99 times out of 100. And once again, there's the schematic for our drawing that shows you our PCB gate drive here. And this is where it's monitoring the desaturation. I think on the next slide, we zoom in on that a little bit. Yep, there we are there. So it's monitoring the collector and the emitter for these two IGBTs here, which would be called the top IGBTs. And then it's measuring the collector and the emitter for these two IGBTs here. And if either of those go above 9 volts, then it switches off the gate to both of those IGBTs and gives you a desaturation alarm. So what are the benefits of a DPP bridge? Well, first of all, it's modern technology that provides a near-perfect sinusoidal waveform that has much tighter regulation. So the output of a DPP, an AMETEK DPP system, has a much nicer output with tighter regulation. It's also more efficient because on the ferroresonance system, we do have to put the transformer into its saturation region, and that there's a lot of energy losses in that. It does run hot. So the PWM system is much more efficient. It has a smaller footprint because it doesn't need the bigger CVT. It still needs an isolation transformer, but the filter is smaller and the normal transformer is slightly smaller, so we can have a smaller footprint for the DPP system. We can have a much wider range of alarm options and monitoring points as part of the standard package because it's all digital electronics, and we are monitoring so many different things inside the DPP to create that PWM waveform. We can get much more options on the system. It also enables greater flexibility for communication, especially through Ethernet and Internet, and it has much better dynamic response to load steps. So if you have a system that you know is going to be connected to loads that have large load steps on it, you would be much better to have a PWM system, which is our DPP UPS, rather than a ferroresonance system, which doesn't react as well to big load steps. And then our final slide is the comparison between the two. Okay. And unfortunately, on my page, it's very difficult to see. So I'm going to switch my whiteboard off, if you give me a moment. So the first column is for the CVT system, and the second column is for the PWM system. So for technology, for a CVT system, it's simple and reliable transformer technology that regulates the voltage. But for a PWM system, it is modern and uses rapid electronic switching to control the output. So for the CVT system, the technology is robust and proven, although the output is not as nice. For the PWM system, it's modern, uses rapid electronic switching and control boards. So it's a much nicer output, but the IGBTs are a little bit more sensitive. The efficiency. The CVT system is generally a lower efficiency, especially under low or varying loads. For the PWM system, it's much higher efficiency with power loss only during the brief switching transitions. So it's a much more efficient system, the PWM. For the output system, the CVT is a modified square wave that has higher THD. For a PWM system, it produces an output that closely resembles a pure sine wave. For us, it's an 8 kilohertz system, which has very low THD and averages the pulses. The voltage control for a CVT system, the transformer provides the constant voltage due to its saturation mode, and it's very, very simple. It just does what it's designed to do. The PWM has precise control over the output voltage and frequency, but it's much more complex electronics to do that. There's additional control boards, processors, and all that kind of stuff. Size and weight. The CVT system is bulky and heavy due to the large transformer. But for the PWM system, it can be smaller and lighter due to the use of a normal output transformer. Dynamic response, how quickly it changes to load steps. For a CVT system, it's slower to respond to changes in load. For a PWM system, it is faster. Remember we said that it can change the width of every single pulse in that 8 kilohertz PWM, and that allows us to have a much better dynamic response. Reliability. The CVT system is 70-year-old technology. It's extremely reliable. Pretty much we say that it's bulletproof. Very much less complex feedback in electronics. It just works. And in truth, it's still, the ferroresonant transformer is still used in the nuclear industry. In the majority of all of the nuclear power plants in North America, they use CVT technology because they know it works. They know it's reliable, and you get 20 to 40 years out of that UPS. Honestly, we truly have UPSs out in the field that are 40 years old or more that still work to this day, that we work on an annual basis. They are just so reliable. For PWM systems, it's newer, more complex technology, and it's the benefits unfortunately give you more to go wrong because it's just more complex. But it is in truth, it's better technology. And the last thing is the noise. The CVT system does produce audible noise. It's a 60 hertz low frequency hum, which is quite audible and some people say is slightly annoying. I actually like the sound of them, but that's me. For a PWM system, it's a high frequency electrical noise, and it does generate EMI, which requires filtering, which we take care of. But the audible noise is a high pitch 8 kilohertz, which a lot of other people say is quite annoying too. So it depends what frequencies your ears are sensitive, I suppose. So that is a comparison between the two. So hopefully that gave you a good indication of the difference between the PWM system, which is our modern system, and the ferroresonance system, which is our older, more robust system. So now I'm going to go over to the chat bar and see if we have any questions. I don't see any questions. So if you do have any questions, please put them in the Q&A section now. And while I say thank you to everybody, I'll give you an opportunity to type in there. And if I see anything come up, I will answer it. But while I wait for any questions, you can see in the chat bar that London has put a link in there that asks you to take a 2-minute survey. The reason why I did PWM versus CVT technology today was because somebody on one of our surveys asked us to go over that. So I read every single survey, and I think it's question 5 in the survey that asks, what topic would you like the next webinar to be on? So I saw that on one of the surveys, and that is why I did it this month. So if you do want us to cover a certain topic, please fill in that survey following the link. It's a very, very easy, quick survey, and tell us what you would want in the next webinar. Okay. Also, London has put in all our contact details. So you have our link to our website and our contact us page. You can fill out that contact us. That goes to our marketing department, and then the marketing department will forward that to the correct person to deal with your question or concern. We also have our email address, which is monitored, sci.marketing@ametek.com. Once again, that will be sent to the correct person to answer your question. And then this webinar will also be uploaded to our YouTube channel, and London has put the link to our YouTube channel underneath there. So that gives you, and don't forget, you can also call us as well, 1-800-635-7300. You will get to a human. There are a couple of menu trees you have to go through. We have to know what region you're calling from. And then you will get put through, during normal working hours, you will get put through to the direct technical manager who is responsible for your region. If it's after hours, it goes to our after hours team, and they will send that message out to the correct technical manager on duty, and they will get back to you usually within an hour or so. Hector has asked, will we be providing links to any of the white papers you referenced? So if you use that link that London's put in there, that's https://solidstatecontrolsinc.com contact us page. If you go to that page, you'll see at the top, it will have a white paper tab. And in that white paper tab, it has all of the white papers that I mentioned today, especially the one about how the CVT actually works. And it definitely makes good bedtime reading. The magnetism and the capacitance and all that kind of stuff. It's explained very, very well, but in my mind, it's very complex. Electricity is hard enough, and then putting magnetics into it just makes it even more complicated. Personally, I like to look at a CVT. Thank you, London. There's a direct link to the white papers. God, aren't you awesome? So thank you for that. But the way I like to look at a constant voltage transformer is you put varying voltages in and you get a constant voltage out. It's as simple as that. Tao has said, is there any derating that has to be done for either ferro or PWM based on the load types? Not in general, except for if you are adding inductive loads. So if you are adding motors or fans or anything that has, basically it's an inductive load that has an inrush current, then yes, you will have to do some derating. But that's the same with any UPS. If you connect a transformer to any system, you know that the inrush to that transformer could be 4 times the rating of the transformer. So if it's a 100 amp transformer, you could see 400 amps when the transformer is energized. So you then have to design your switch gear to supply that. And the UPS is exactly the same. It's if you put a motor or a transformer on the output, if you have a 100 amp, which is a 10 kVA UPS basically, and you put a 100 amp motor, then you're not going to be able to power that from the UPS. You're going to have to put in a 40 kVA system to allow for that inrush. So you do have to do some derating based on the loads, and it's not exactly derating. You actually have to increase the rating of the system. Okay, hopefully I explained the question. I mentioned the size of a load steps being a reason for using DPP over the CVT. Is there a rule of thumb on what that would be, a percentage of the total capacity? I don't, Hector, and that's a very good question. And maybe somebody from the factory, I'll ask that question to the factory and see if I can get back to you with an answer for that. Because I truthfully, I don't know. Because it's very unusual. The only thing that tends to, that we have seen recently that causes issues on our ferro systems is if you have a large batch of process analyzers connected to the output of the system, because the analyzers usually have heaters inside of them to monitor whatever the gas or fluid that they're monitoring. And when all of the banks of those analyzers, the heating banks, come on at the same time, that is a very peaky load. So that can cause issues on our ferroresonant system. But I don't know a percentage. I do know that we have a crest factor. So we say that you can't have a crest factor of 3 or more, which is the RMS versus ratio compared to the peak of the current waveform. And we can't have a crest factor more than 3 on the ferroresonant systems. I can't remember if it's smaller on the DPPs. But I'm rambling a little bit, Hector. I will see if I can get you that answer for after this conversation. Well, I don't see any more questions, and I've given you all the links that you need to follow up with us on. So all it leaves me to do is say thank you very, very much for joining us on this webinar. That is the exact 1 hour mark. So I did pretty good today. It just lasted 1 hour. Thank you to London for putting all those links in. We really do appreciate that. And don't forget to fill out that survey. And we will be skipping December. There will be no webinar in December, but we should be back to it in January. Check your emails for when that will be. So enjoy Thanksgiving if you're in America, and enjoy the holidays when they come. And I look forward to talking to you again soon. Thanks very much, everybody. Take care.